All right, greetings everybody. Just gonna wait a few more seconds here. Let everyone give everyone an opportunity to join. All right, so my name's Devin Vance. I'm one of the senior support engineers over here in the U.S. offices at LINBIT. I'm joined today with Moritz, who's uh, the LINSTOR Operator developer over in Vienna, Austria. Today we're going to be talking about the LINSTOR Operator. Today's demonstration is not going to really talk much on LINSTOR itself. I feel like that was covered in some talks earlier in the LINSTOR Days program. And if you didn't get a chance to check those out, we should have videos of those available sometime next week. Okay, so let's go ahead and get started. Before I go into too much detail on the LINSTOR Operator, I want to take a quick moment and talk about LINBIT and its history and who we are. So our first product came out in early 2000. This was developed by our still CEO, Philip Reisner. This was DRBD, which is a block level replication tool within Linux, primarily targeting high availability clusters. DRBD is still very much a cornerstone of LINSTOR and how LINSTOR itself achieves replication. So 2001, we became a company in Vienna, Austria. We were actively selling support for DRBD, but also providing general purpose Linux IT support at the time as well. Fast forward to 2007, our disaster recovery product, DRB Proxy, was developed. This is used for long distance replication asynchronously with DRBD Proxy. You can replicate now anywhere in the world. Then a year later in 2007, we opened an office in the United States, or 2008, sorry. And we also rebranded as well to primarily support the software we developed and less of the general purpose Linux IT support. In 2010, that was 2633, DRBD is merged into the mainline Linux kernel. Pretty soon afterwards, we see a large tick in the number of installs and downloads. And then in most recent years, we recognized this need for persistent storage in container environments, particularly alongside the use of Kubernetes. So we developed LINSTOR. It's important to note LINSTOR isn't specifically built for Kubernetes, though, but rather is a framework for resilient Linux storage management. Naturally, it's the backbone for our Kubernetes operator, but it can be used in other environments as well, such as OpenStack, Docker Swarm, and others. And then most recently, LINSTOR just recently became a OpenShift certified operator for use in Red Hat's branded Kubernetes. So real quickly, for those maybe who aren't aware, I just want to briefly touch on what a Kubernetes operator is. Kubernetes operators came onto the scene in late 2016. They were introduced by the CoreOS team, and the first ever operators were for etcd and Prometheus. And the goal here was to help package and distribute cloud native applications. Oftentimes, I feel like when someone's referring to cloud native apps, they're simply just talking about an application that can be managed by an operator. Operators themselves consist of two primary components. That is the operator controller. Works pretty much the same as the rest of Kubernetes. It relies on a desired state, a present state, and a never-ending reconciliation loop. And then you have your custom resource definitions, which are custom API objects that extend the functionality of Kubernetes, specifically for the operator and application. This is essentially where we can record and edit the desired state. And here's a quick little graphic of kind of how that looks. You have your reconciliation loop within the controller. The user would update a custom resource. This change affects the desired state. The desired state adjusts the present state, and the present state's tracking the desired state. And yeah, the controller is also constantly tracking these custom resources. Just a never-ending reconciliation loop, just exactly like you'd find at the very core of Kubernetes itself. So what are the custom resources at the heart of the LINSTOR operator? We have the LINSTOR controller, which configures and deploys the LINSTOR controller. The satellite set, which configures and deploys all of the LINSTOR satellites. This runs on all worker nodes, ran as a daemon set. And then we also have the LINSTOR CSI driver, which configures and deploys the CSI driver. This is what translates everything from Kubernetes to LINSTOR. But I mean, you really, in most use cases, shouldn't have to interact with any of these things because of Helm. So Helm's often advertised as the Kubernetes package manager, and I personally feel it does a great job at doing just that. While I previously said that operators also serve as a kind of package for cloud apps, Helm really completes that deal here. So our LINSTOR operator will include everything, all of the components of LINSTOR, but LINSTOR itself has some dependencies, primarily etcd or some type of backing database or value store. And Helm will install that as a dependency of us, and it also will install extras or add-ons that extends LINSTOR's functionality, most recently and specifically Stork. And Helm also helps with removals and upgrades as well. And enough talk of all this, though. Why don't I hand it over to Moritz, and he can show us all of that in a demonstration he has prepared for us.
Yeah, thank you, Devin. So, hello, my name is Moritz Wanzenberg. I'm here in Vienna, Austria. I'm the primary developer of the LINSTOR operator and all different kinds of Kubernetes integration. And I just want to show you a quick demo of how you can use Helm to install the LINSTOR operator, how you can provision volumes, and basically show you what you can do with these volumes. Like you can create snapshots and you can expand volume size and so on. And yeah, with that, I've shared my screen. I'm currently connected to my test cluster containing 3 nodes. And as you can see, there's currently nothing really running on this cluster. I've just reset it, completely new setup. And yeah, as Devin already told you, we prefer to use Helm as our package management for Kubernetes, and I've already got the Helm binary also installed here. So we will put that to good use. Now, before we actually can install the Helm, the LINSTOR operator, we need to add our LINSTOR repository to Helm. So it's charts.linstor.io. And if you can take a look and see all the different charts. Charts are basically packages in Helm speak that we provide. And you can see there's the LINSTOR operator itself. And then we also provide you with a helper path. So before we can actually install LINSTOR, we need some kind of persistent storage for LINSTOR itself. So this can be either etcd or some existing database. And for ease of use, we want to provide you with a quick start to get started with etcd. And so you can, or the LINSTOR chart itself will include etcd if you want to, but etcd itself needs persistent storage, and this is done using this helper chart. Another thing we need before we actually can install anything is we need access to the drbd.io Docker registry. So we'll just quickly create a pull secret so that we can pull all the required images for LINSTOR and all the different Kubernetes components we want to install. So let's quickly create the secret of type Docker registry. Let's call it drbd.io cred, and then we need to specify, okay, it's the DRBDIO server and username. I'll use my own account for this. And I've hidden my password behind an environment variable so that you don't have access right away. Yeah, so now the secret is created. Second step is we need actually some persistent volumes to start with, as I said, for our etcd. This can be done by first taking a look at all the different nodes we have available. So I've got 3 nodes available here, and I want 1 persistent volume on each of them. So I can quickly use our helper chart. So helm install, then I need to give this installation a name that I can then later reference, or that if I want to delete it, for example, then I can give this name. And then I reference the chart I want to install. And this is host path. And then I'll need to provide it some values. In this case, I want to say on which nodes I want to install it. And I'll just use all of them. And Helm will take care of creating the resources, so the persistent volumes claims, and also ensuring that all the right permissions are set on these host path volumes, because we take great care that basically our containers are not running with permissions they don't need. And in this case, we'll make sure that etcd does not run as a root user. So this also integrates, for example, with OpenShift and with pod security policies if you're using that in your Kubernetes installation. So now we've got 3 persistent volumes, and now it's basically time to get started. Everything's set up for our LINSTOR package to be installed. There are a great many customization options available for the LINSTOR chart. Just show you what that would look like. Most of them you don't really need, and they are usable defaults. But if you want to tweak it, you can. I've just made a few small adjustments to the default values, and I'll quickly show you what I use. So first of all, we've referenced the Docker pull secret that I've created before here. Then for our small cluster of 3 nodes, Stork is not really needed. It would basically be just another set of pods that's running in the background, but not really providing any value for this demo. And then last but not least, or perhaps even most important of all, we need to set the right kernel module injection image. So one component, the LINSTOR satellites themselves, need access to DRBD. DRBD is a kernel module, and this is most likely not installed on your Linux, on your base operating system. So we provide you with the required kernel modules via these images, and this depends on what your host operating system is. And my test cluster is running on Red Hat Enterprise Linux 8, so I'll use the matching kernel Docker image from DRBDIO. So these are the changes I wanted to make, and now I can just again type helm install and reference the values I've just shown you. And Helm will take care of creating all the right deployments, creating the custom resources, which we'll take a look at shortly. And yeah, so now everything's ready to set up. Now we can take a look at all the different components that are started. Not just the pods, even everything. So right away, 3 components spawned by or created by Helm is the LINSTOR etcd instance, which is used by, or which is basically a dependency. So it's a prerequisite for LINSTOR itself to work. Then there's the LINSTOR operator, the heart of our Kubernetes integration. And right now the operator already created all the other components. Talk about that shortly. And another basically dependency installed by Helm is the snapshot controller. So we include a snapshot controller that you need for volume snapshots in Kubernetes to work. In most, basically, in most commercial distributions or supported distributions of Kubernetes, this is already included. So in OpenShift, it's already included. If you're running some kind of Google Kubernetes cluster, then it's also most likely included. But if you're running a basically naked Kubernetes installation like I do here, then you need a snapshot controller for volume snapshots to work, and we'll include, or we'll set that up for you too, if you need it. And yeah, now to the other components created. These are created by the LINSTOR operator itself. So first of all, there's the LINSTOR controller here. And this is the heart of LINSTOR itself. So that's the brain of the operations. And the LINSTOR controller provides a REST API and in turn talks to the LINSTOR satellites. So there are 3 LINSTOR satellites running, 1 on each node. And the LINSTOR satellites are responsible for creating the right resources for DRBD and setting up the local storage for LINSTOR and so on. And then another part is, or the last part is the CSI components. So all of these here. This is basically the bridge between the CSI interface. So CSI stands for Container Storage Interface, which is the default, which is the Kubernetes storage plugin interface. So every storage provider basically uses this CSI interface, and these components here do the translation between Kubernetes persistent volumes and LINSTOR volumes, resources, and so on. So yeah, with that, everything's up and running. And we'll quickly take a look at the custom resources that we have available. For example, the LINSTOR controller resource, which is basically a normal Kubernetes resource. So you've got your spec, which is your wanted state, and this is the operator will try to achieve it. Right now here, there's a lot of default values and unset values because the default installation just works. But you can see here, we've also got some status output. For example, the controller is running, it's registered, there's satellites connected, they are all online and registered, and there's some additional information. Also important always, there are currently no errors, so everything's working as expected. Then we have got the LINSTOR satellite set. And basically the same thing. You've got your wanted state, your spec, and then you've got your status. And here we see also everything okay, everything's online as it should be. There are currently no errors. And the last component is the LINSTOR CSI driver. Again, there's a spec, and we pull in lots of upstream CSI components and our own LINSTOR CSI plugin. And then there's also a status, okay, the controller is ready, the nodes are ready, no errors, so you're good to go. We can start from CSI points of view, everything's ready. We can start creating volumes. One thing we can do is we can also take a look at how this looks on the LINSTOR side of things. So we can quickly execute the LINSTOR client on the LINSTOR controller, and we'll see that there's also a lot of interesting information here. So currently the LINSTOR itself knows about these 3 satellites. So all my Kubernetes nodes have a satellite on them. And then there's also the controller itself. We can find out more about these, about the nodes or about our satellites, for example, which storage backend they support. So we've got the logical volume manager is available, but for example, no ZFS because the needed kernel module for that is not available. And we'll also see DRBD is loaded. We could use encryption if we wanted to. We could use NVMe over Fabrics if we wanted to. So yeah, here you can see a bit more information about what the nodes can actually do. Yeah, so for LINSTOR itself to provision volumes, we need to tell it where the data can actually be located on disk, and this is usually done using storage pools in LINSTOR. If we take a look at the currently available storage pool in LINSTOR, then we see that there's actually none available. You've got this diskless pool on every node available, but this is only used if you want to attach to a remote storage device. So if demo 1 would need to attach to a storage device from demo 2, then it would use this diskless pool, but currently since there are no other devices, that doesn't really work. Another cool tool from LINSTOR side is the physical storage command, where you can see, we can quickly check if there is any storage device which you could use as a basically backend for your storage. And if we take a look here, we can see that on all of the Kubernetes nodes, there is a device available, which has around 50 gigabytes of free space. And LINSTOR will only pick this up if there is no other information on that volume. So it's not mounted anywhere. There's no partition table on there. So it will only use this device if it will only show this device if it's empty. And now we can use our Kubernetes integration to actually set up a storage pool on this device using Kubernetes resources. So we'll quickly edit the satellite set. So in here, there's our spec. And in the spec, there's the automatic storage type, and it's currently set to none, so no automatic storage will be set up. We can change that to a lot of different values, for example, LVM, or in our case, we want LVM thin, so thinly provisioned logical volumes. And if we apply this, we should quickly see that we have a new storage pool available. And now every device has a new storage pool, VDB, using the LVM thin driver and around 50 gigabytes of free space. It supports snapshots, everything's looks fine. And now we've got our storage sorted out. We can start with our persistent volumes. So first of all, we need Kubernetes, or we need to tell Kubernetes that the LINSTOR, that we would like to use the LINSTOR driver for our persistent volumes. The way we can do this is using storage classes, a normal Kubernetes object. We provide a name. In our case, we want to say it's LINSTOR 3 replicas. it's using the LINSTOR CSI provisioner. So this is the part where we tell Kubernetes to use our LINSTOR CSI driver. We allow volume expansion, so you can later edit your persistent volume claims and resize them if you want. We want to use the storage pool we just created, and then there's the autoplace 3. So LINSTOR can replicate data across different nodes, so that if one of the nodes goes offline, this data is still available on other nodes. And in this case, autoplace 3 means that that everything will be replicated across at least 3 nodes. So yeah, that's this parameter. And then there's the resource group. So resource group is a LINSTOR concept, and in principle, it's the same as a Kubernetes storage class. And so we just, so for traceability, we'll name it the same as the storage class here. So this we can then apply, and then we can create our first persistent volume claim. So again, normal Kubernetes resource, we just tell it to use the just create the storage class, and Kubernetes then knows that it will use the LINSTOR CSI driver. We'll use read write once as access mode, and we'll request 500 megabytes of storage, and we can apply that as well. And in a short amount of time, our persistent volume claim should be bound. Now it's bound to a volume, which is provisioned by LINSTOR itself. So how does this translate into LINSTOR, into the LINSTOR world? So we can take a look at the LINSTOR. In LINSTOR, there's now a resource definition for our persistent volume claim. And this resource definition has many resources, one on each node, and they're all in okay state, and all these resources correspond to a specific volume on each node. And on all of these nodes, there's now a device called DevDRBD 1000, which is backed by our storage pool, so backed by LVM thin. And because it's LVM thin and we haven't actually written anything yet, it only takes like, I don't know, 206 kilobytes, and everything's up to date, which means, yeah, it's, since we haven't actually written anything, there's no data to replicate yet. Okay, and now that we've got our persistent volume, we can start using this volume. In a pod, I've just created a small demo pod, which doesn't actually do anything. It will just wait until I'll execute into it. And we use our created persistent volume claim here and mount it to mount data. So let's quickly apply this. And then we can take a look if it's already started. This will take some time depending on how the Kubernetes API feels, and I've missed a pod in here. Okay, so now our pod is running, and I'll first of all again want to show how this looks in LINSTOR. So now in LINSTOR, the resource is marked as in use on demo 1. So our pod is scheduled on the node demo 1. And it's attached to this volume, and it's in use. So no other volume can attach to it currently, so that we don't have to synchronize reads and so on. So that's one thing. And now I actually want to show how it looks like inside the pod. So I'll quickly execute to this pod. We'll change to data directory. So this data directory is using dev.drbd 1000. It has a size of around 500 megabytes. It's a bit less because we need the file system metadata and so on. And yeah, so we've got our volume set up here. We can then write anything we want into a file right here in this directory. And we've got this file, everything's written fine, and I'll quickly jump out of here. If you take a look again at the volumes just created, again, this volume is in use. But now, since we've actually written some data into it, it's the allocated size increased a bit. Yeah, so one of the main advantages of LINSTOR is this replication that we provide across volumes, across nodes. So to simulate this, I'll just quickly delete this pod and try to access the same persistent volume from another node. And then we'll see that all the data is replicated and there's no problem using this volume from another node. Okay, so now it's deleted and we'll apply, or I'll quickly show you. There's a second pod, which is basically the same as the first pod, but I'll here force it to be scheduled on pod, on node demo 2. And if we then apply this and wait for it to start. It's already running. Then gonna jump in here again, mount data, and there's our file we created from the other pod. It's replicated on a different node right now. So yeah, again, from LINSTOR side, we can now see that the volume on demo 2 is in use and the volume on demo 1 is unused, and will replicate everything from the demo 2 host. So that's it for the most basic demonstration. Now I want to use LINSTOR itself to host a bigger application, or to use a real application. So for this demo, I've chosen MinIO as our example. MinIO is an object store, and compatible with Amazon S3, and will create a persistent volume that's used by MinIO to store its data. We will create a backup using volume snapshots, and then also show how we can restore it. So luckily, MinIO is also available via Helm. So I'll quickly add the MinIO repository. And now we can see that MinIO is available as a chart, and I've also created a few customizations for this MinIO deployment. So first of all, I'm using the node port service so that I can show you what the web interface for MinIO, or what the web interface will look like using my local browser. I'll create a default bucket just so that the demo is quicker. And the real important part is here we can configure the persistence, and layer of MinIO, and we'll say we want to use the LINSTOR storage class I used before with relay replication across all nodes in our cluster. And we'll use an initial size of 10 gigabytes for our storage. So with that, we can quickly install MinIO using our customization. And in a few moments, the Kubernetes API should be ready to start MinIO, and soon after that, hopefully ready to serve MinIO. And taking longer than usual, but I guess it's fine. Okay, so now it started. Everything's ready. There's now a new persistent volume claim from MinIO with the size 10 gigabytes and using our LINSTOR storage class. And also there's a new set of volumes in our LINSTOR view. In this case, MinIO is scheduled to run on host demo 3, and it's currently in use and already using lots of space for being basically empty. And now I can quickly switch to my browser and open the MinIO site. And in here, normally there would be something to download, but I actually, since it's empty, there's nothing to download yet, but I can quickly add some example files in here, just so that we have some content to look at. So now I've uploaded something to MinIO, and it's persisted that in our LINSTOR volume. And right now, LINSTOR, this relay replication doesn't protect us against basically normal data deletion. So I could go here and delete this file, and basically this deletion would replicate across all 3 nodes, and I wouldn't be able to get back. This is where snapshots come in. So LINSTOR itself supports snapshots. Currently, we don't have any snapshots, but luckily we can create some using normal Kubernetes resources. So for snapshots in Kubernetes, you need a snapshot class. It's like volume class, storage class, but for snapshots, in which we tell Kubernetes that our LINSTOR CSI driver is also capable of handling snapshots. And we just apply this snapshot class. Then we actually want to create a snapshot of our volume. And this is done using volume snapshots, in which we give the snapshot a name. We say that we want to use the snapshots class we just created, and then we need a source. And in this case, we want the source to be our persistent volume from our persistent volume claim, MinIO. And so we can apply this one as well. And now this, depending on your API server, this may take some time for the snapshots to propagate, but it shouldn't be too long. So right now the Kubernetes API tries to create the snapshot, but it's not yet ready. If we take a look at LINSTOR, the request for a snapshot hasn't actually reached the LINSTOR API yet, but now it's here. Now we have a snapshot of our persistent volume, and the snapshot was successful. It's available on all of these 3 nodes. For Kubernetes, this means that the snapshot is now marked as ready to use. And now I can again go to the web interface, and let's say I accidentally delete every file in here. So now no files are available. Even if I reload, there's no file available. So to basically restore from a backup in Kubernetes, you need to create a new persistent volume with the snapshot as a source for your persistent volume. And this looks like this. So it's a normal persistent volume claim, which is basically the same persistent volume claim as the original min.io. I've just called it min.io restored, and I've specified as data source that our snapshot should be the data source. So it will be on creation, the volume will be filled with the contents of this snapshot. And let's quickly apply this one. It's also already bound, so it's ready to use. And just to show that snapshots really work, we'll quickly edit the min.io deployment to point to our new restored volume. So in here's the volume part. This is the old min.io volume where I deleted all the files, but now I use min.io restored to change the persistent volume we use. And then I'll just need to wait until the deployment is ready, and it's actually currently still in progress. And now the old pod is terminating, the new one is already done. So if I go back to here, if I refresh, all my files are back because I've restored them from the backup. So, and the last thing I want to show you or to demonstrate you is volume expansion. So again, using our min.io example, let's say we're using right now the min.io restored claim. And let's say the 10 gigabytes is not enough for us because we've stored so many files in our storage. So if I just edit this spec right here and change this one to 20 gigabytes, then since we allowed volume expansion on our storage class, Kubernetes is fine with this. And again, depending on the speed of your Kubernetes API and how all the some timings of the different components, we'll soon see that now there's 20 gigabytes of space available here. And I'll just take a last look at LINSTOR itself. Right now, we are using this restored volume right here, and it's actually gotten a lot bigger, but it's all up to date. And take a look at the volume definition, and it's marked as 20 gigabytes, and everything's working as expected. And yeah, with that, I've basically come to the end of what I wanted to show. I'll hand back to Devin.
All right, thanks, Moritz. Let me go back to sharing my screen here. Okay, so I mean that was a pretty lengthy demo, covered a lot of the bases here, but if any of that piqued your interest, I'd encourage you to check out some of our community resources. Feel free to join our mailing list or our Slack community. check the documentation or see the code. You can get access to all of this at LINBIT.com. We also have some more talks as part of this LINSTOR Days series. You can find the full schedule also at LINBIT.com under the LINSTOR Days tab. And as I said, this presentation as well as the other ones should be recorded and available hopefully sometime next week. So we have a few minutes left here. We have a Q&A feature here in the Zoom webinar. A couple questions have been asked, so I'd like to address those now. But if you have something you'd like to ask, please feel free to get it in there. But again, if you have a question later, you know, shoot us a message. Most of us hang out on the Slack. So earlier we had a question here from Americ asking if we have any plans to support HashiCorp's Nomad. I don't know if that's something we need yet to discuss here. Not sure if there's any official stance on that. Honestly, I'm not too familiar with HashiCorp's Nomad. If it supports the CSI, as we also support the CSI, it may just work. But again, I don't think that's something we've looked at yet in any official stance. An anonymous question here we have is, can we clear creation of the lost and found folder after persistent volume is created? Avoids us having to clean this via init containers later on. LINSTOR should just make the block volumes. The lost and found folder is going to be a function of the file system you choose. So yeah, I feel like you'd have to handle that somewhere else, possibly at the pod creation. But yeah, LINSTOR is purely block storage. Does the LINSTOR operator, can it be used for migration from a no provisioner kind? Moritz, you got any thoughts on that one? I'm not sure if we're asking if you can migrate from something with ephemeral storage to LINSTOR.
No provisioner. We don't have any support for that right now. So
okay,
something to look into.
Okay. What are the read-write speeds achieved during performance run? I mean, it varies widely from the storage subsystem, but we just do the block storage. It's fast. Granted, there is a little overhead you get from the replication and whatnot, but we did recently set a performance record with over 14 million IOPS. That was with hardware provided to us by Intel. So fast. It can be very fast, but again, things vary as storage subsystems vary widely. I see the controller talks to satellite nodes. Do you support encryption?
Yes, we do. So all communication, so the LINSTOR controller itself also has a REST interface, which if you want to, you can integrate with however you want. This supports encryption. We support encryption to our backend or database backend, so for etcd, and there's also encryption support between the LINSTOR controller and the satellites, if you want to.
And that uses, I think, TLS, correct?
Yep. Yeah.
Perfect. Someone here asked, is the data replication synchronous? Yeah, that's fully synchronous, all handled via DRVD, which, as I mentioned earlier, has been around since around 2000. But yeah, it's going to be fully synchronous, handled in kernel.
I mean, if
asynchronous is, oh, go ahead.
It's an option right now. Yeah. So you can configure it to your liking if it's synchronous or asynchronous, I think.
Default synchronous, though.
Yeah.
Yeah. in case of dire emergency, is it possible to access the file system within a DRBD device without starting DRBD? I'm going to say, yeah. So DRBD by default puts its metadata at the very end of the device. We're using, in this demonstration, we used LVM thin. So if you absolutely need to, you can definitely go to one of those hosts where there was a replica and just mount that LVM thin volume, or maybe even smarter, you can make a snapshot of that LVM thin volume and mount that read only to try and do data recovery without actually altering anything on the disk in a situation like that. So, why did volumes on the different nodes in the last step have different used data values? I believe that's just because of the LVM thin and the way it's the way it consumes, storage, the thin provisioning. I don't know if you want to maybe.
Yeah, that's an artifact of how we restore, how we currently restore, or the order in which we currently restore the volumes. This is something I want to look into. It's always bugged me a bit that the different values reported. Yeah. So in theory, it should always be the same. Yeah.
But yeah, that's a side
but
effect.
It doesn't compromise the working or the volumes itself. It's just not so nice.
Yeah, that's a functionality of the LVM thin provisioning. Yeah.
Yeah.
Yep. Does replication compromise IOPS? There's a blog post where we go into more detail on when we're announcing the record of the 14 million IOPS, and it talks about that in more detail. But I mean, since we replicate fully synchronously, we need to, confirm that stuff is written to the disk on the peers. So as I mentioned earlier, replication does add some overhead and will slow things down a bit, but depending on how fast your hardware and your network is, it's generally pretty minimal. Okay, I think this one. So in diskless mode, can we write on primary node and then promote another primary mode? Does this step depend on controller? Can users promote another primary manually, as with DRBD now, in case controller is down? So I mean, it's currently still just read write once. I mean, trying to access the same block device in multiple places without some cluster aware layer there between is dangerous and a quick way to scramble up your data. So presently, right now, it's just read write once. Diskless is used for attachment to a DRB resource over the network where the storage isn't available locally. So like in our demo, we only had 3 nodes and we placed 3 replicas, so everyone had a local copy. But say I was doing 3 replicas and I had 9 worker nodes, I could still schedule a pod where there wasn't a local copy of that data and attach to it disklessly. So that's pretty much the purpose of that default diskless pool. Can user promote another primary manually with DRB now in case the controller is down? Yeah, that's good, important to mention. So the LINSTOR controller, while it is kind of the brains of LINSTOR and it knows the state of things and it alters the state when you want it to, if it's ever down, everything underneath it is pretty much in kernel, LVM, DRBD. It can still function, completely even with the controller down. Couldn't really necessarily provision new volumes, but the present volumes will definitely still be there. And if you really needed to, for some odd emergency situation, you could definitely manually promote one of those resources if you needed to. Can't really think of a situation where you want to, but you could if you needed to. is it possible to replicate the volume simultaneously to a DR site? I mean, I know in theory it's possible. Moritz, I don't know if the operator has any functionality for that.
There's no specific, no specific integration right now. There's talk about it, but nothing made it into the operator just yet.
Okay. I mean, DRBD can do it with DRBD proxy. So, I mean, in theory, you might be able to pop open the hood and do it from in there. But yeah, the operator doesn't support any of that functionality. What happens if you lose the controller permanently? How do you recover from this? So, I mean, ideally, we're using etcd to back that. And we're setting up etcd with persistent volumes as well. So etcd replicates amongst itself. So ideally, you'd have multiple copies of that etcd key store. So if you were to lose one node permanently, you could just schedule a new controller pod somewhere where there's still a copy of that etcd key store. So that's the plan for recovery there. Can users run multiple controllers? No, you should only have one. It's kind of the centralized brains of the whole LINSTOR thing. But I mean, that's run as a stateful set. So ideally, if for some reason the node it's running on goes down, it should be scheduled somewhere else, at which point everything should resume operation normally.
Just to add to that, there's actually now a mode where you can start the LINSTOR controller as multiple copies. This is basically, there's only ever one active LINSTOR controller, so you only ever talk to one, but in case that one goes down, another one would quickly take over, like in 20, 30 seconds. So you would lose basically the possibility to change the current state of the cluster in these 20, 30 seconds, but after that, everything should be back online.
Right. Okay, we got another question here. In case of two replicas, I recall a possibility to use a third diskless node as an arbitrator. Is this available in the Kubernetes operator? I think he's referring to DRBD's quorum functionality. Do you want to elaborate on that, Moritz?
Yeah, to my knowledge, that's all available. Everything that's available in LINSTOR in that regard is also available. It's, what's it called? Auto quorum. I'd have to check right now.
Believe it is, though. Okay, looks like we got one question left. Is it possible to share the same etcd instances that Kubernetes uses with LINSTOR? I know it's definitely not advised. I'm not sure if it's possible or not.
It's possible if the etcd endpoints are available from inside your Kubernetes cluster. So you can manually, or you can configure the Helm chart to not provision its own etcd, and then you need to change the etcd endpoint the controller wants to connect to, or the etcd endpoints the controller wants to connect to. And if you point that at the Kubernetes etcd, then it will work. If that's a good idea or not, it's a highly debated topic, and I don't know. I don't want to give an opinion on that, because I've seen both recommendations that you want to do that and recommendations that you shouldn't do that. So yeah.
All right. Okay, well, if we all right, if there's no more questions, like I said, I definitely encourage you to check out our website, linbit.com. From there, you can find some links and resources on how you could, try out the LINSTOR operator yourselves. So yeah, please look us up and make sure to check out the rest of these presentations as part of the LINSTOR Days series. So if there's no more questions, I want to thank everyone for attending, and hope everyone has a good rest of their week.